Hi, everyone. Let's apply these identities to calculus. This is an optional section. So I'm going to claim that if f of x is sine of x, then the derivative given by f prime of x is cosine of x. The derivative of sine of x is cosine of x. And likewise, the derivative of cosine of x is the opposite of sine of x. Now remember what the derivative is. We start with slopes of secant lines, indicated by this difference quotient, rise over run. You may remember this from 1.11. This was an optional section in chapter 1 about derivatives in calculus. The slope of the secant line is given by rise over run. That's the average rate of change of the function f on this interval. If we let h approach 0, if we let the run approach 0, the slopes of the secant lines will approach the slope of the tangent line in red. And that could be either from the right or the left. H could be positive or negative. We let h approach 0. And here's the limit definition of the derivative function. You'll see this in calculus. F prime of x, the derivative function rule, is the limit of this difference quotient, the slopes of these orange secant lines, as h approaches 0. If this approaches a number, that's the slope of this red tangent line, the derivative of the function at x. So basically, it's a slope function. The slope of the tangent line, the derivative at x, is kind of like the slope of the curve at this value of x. Okay. I'll show you what I mean. Let's go to Desmos. How do you graph y equals sine of x? You better know this. This sine wave. It's odd, and it goes to the origin. How do you graph y equals cosine of x? That's in purple. I claim to you that the derivative of sine of x is cosine of x. In other words, the cosine graph in purple gives the slopes of the tangent lines to the green graph, the sine graph. For example, I'm going to focus on the origin. The derivative of the sine function in green at x equals 0 is 1, which is the y-coordinate, the cosine value up here on the purple graph. Cosine of 0 is 1. I claim that's the slope of this green graph at the point when x is 0. In other words, I'm claiming that y equals x, which has slope 1, is going to be the tangent line to the green graph at that point. You can see that if we zoom in, this is called local linearity. Yeah, the sine graph, the sine wave basically looks like that line. It's very linear. If you have a derivative, it means you have local linearity. It means that if you zoom in on the graph at that point, you basically get a line whose slope is the derivative. I claim the slope is 1. The derivative is 1, which was the y-coordinate for the cosine graph. Cosine of 0 is 1. By the way, what's a way of seeing that? Let's look at some tangent lines, or secant lines, and how they approach the tangent line. Again, look at that green graph. Let's look at some secant lines through the origin. Through this point and this point, we have this black secant line. Through the origin and this point, we get this blue secant line. From the origin to this point, we get this green secant line. And it turns out that the secant lines will approach this tangent line. I'll put this in red, actually. All right, in red. And the slopes of the secant lines will approach the slope of the tangent line, the derivative. All right, so how do we prove that the derivative of sine of x is cosine of x? Here's the limit definition of derivative. The limit of the slopes of secant lines as h, the run, approaches 0. The run is the horizontal distance between the point of interest and the second point, which we're moving towards the first point. Okay. If f of x is sine of x, then what is f of x plus h? Think substitution. It's sine of x plus h. And how can we express sine of x plus h? We can use a sum identity to expand it. The sum of the mixed up products. And then you have some additional steps in algebra. You use some limit facts. This approaches 0. This approaches 1 as h approaches 0. You get that the derivative of sine of x is cosine of x. I would not hold you responsible for this proof. Similarly, the derivative of cosine of x is the opposite of sine of x. Let's see. Turn this off. Here's y equals the opposite of sine of x. So the cosine graph is in purple. Okay? What's the tangent line up here when x is 0? It's a horizontal tangent line. The slope is 0. That's the value for this function here when x is 0. If you plug in x equals 0, the opposite of sine of 0 is 0. So in other words, the slopes on the purple graph are given by the y coordinates on the black graph. Here, the slope is 0. Here, the slope is -1. Over here, the slope is 0, once again, and so forth. By the way, this is the first derivative of cosine of x. It's the second derivative of sine of x. The relationship is that when the second derivative is positive, this graph is concave up. So when the black graph is above the x-axis, when the second derivative is positive, the green graph is concave up. It curves upward. When the black graph, the second derivative graph, is negative, then the green graph is concave down. It curves downward. That's all calculus. It's all optional, but we needed the sum identities. You'll see much more of this in your calc class.